Okay, these are now let us solve example problems regarding equilibrium of rigid bodies. So we have here, first example, the box wrench in the figure is used to tighten the bolt at A. If the wrench does not turn when the load is applied to the handle, determine the torque or moment applied to the bolt and the force of the wrench on the bolt. Okay. So we have here two forces that is used to or that is applied on the wrench, and then here, as you can see, even if there seems to be a bolt that connects this wrench to a certain fixed wall. Okay, since it is said here that it does not turn, the wrench does not turn when the load is applied, so therefore being a pin section, okay, being a pin support here, it would, as a pin support, okay, it has both the vertical and horizontal reaction. Okay, now the directions of reactions are primarily assumed directions. Okay, and then we'll have here, since it doesn't rotate, so we could also say that it is like a cantilever support, so it also has a moment reaction. So assuming that the moment reaction is acting clockwise, but all of these directions are not yet verified, these are just assumed. Okay, so we will know later if we have the correct if we have drawn the correct direction of the reactions. So we are now going to solve for the reactions, moment reaction, and the horizontal and vertical reaction. So we will be using the three equations of equilibrium. We have summation of force x equals 0, summation of force y equals 0, okay, and then summation of moment equals 0. Okay, so we could say that it is in equilibrium because there is both no translation and rotation that happened on the system. Okay, so for summation of force x equals 0, so we are going to sum up all of the horizontal forces. So we start with ax. So in the equation, we use, or our sign for the ax would be positive since our assumption is that it is acting to the right. Okay, and then we have minus x component of the 52 Newton force. So we have 52 times 5 over 13. Okay, negative because it is to the left, and then we have for the 30 Newton load, we have positive 30 cosine 60. Then this is equal to 0. So what we use is that all of the rightward forces are positive, then all of the leftward forces are negative. So this is what the sign convention is. Okay, we'll just erase this for a while. Okay, then we'll now have ax. So ax therefore is 52 times 5 over 13. Okay, transferring it to the other side of the equation, then we have minus 30 cosine 60. So ax therefore is equal to, you have 52 times 2 times 5 over 13, then minus 30 cosine 60. Now we have 48.57 newtons. So since the result was positive, therefore we are correct that ax really is acting to the right. So we'll also give a direction to the right. So for every reaction, we always give the direction. Okay. Now, we're done with AX. Let's now solve for AY. So we will be using summation of forces y equals 0. So we'll use up all of the upward forces are positive, so that we'll have AY. Okay, positive because our initial assumption is that it's acting upward. Then we have minus 52 times 12 over 13, then minus 30 sine of 60, and this is equal to 0. So AY is equal to, okay, so let's have 52 12 over 13 plus 30 sine 60. Okay, positive na sila because nilipat mo na sila sa other side of the equation. So you have 38.86. This is in Newton. So since the result of AY is positive, meaning that our initial direction of AY, which is upward, is correct. So this is really upward. Okay. Now let us move on to summation of moment equals 0. But the question is, at which location should we sum up moment? Okay, so I believe so that it would be more convenient if we sum up moment at A, because if we are going to sum up moment at A, the moment of AY and AX about A is 0. Okay, so already two of the forces will be eliminated from the equation. But even if moment at A or MA is acting at A, it will still be part of this equation because moment is not a force. So a moment is a moment, and it is always involved in summing up of moments. So let's use positive for all of counterclockwise moments. So we'll start with MA. So since MA is clockwise, we use, in the equation, we write negative MA. We're just following our sign convention. Okay. Now, if you want for MA to be counterclockwise as your initial assumption, you could also do so, and then you will write positive MA in the equation. Okay, so it depends on you. Now, you don't have to worry regarding if the direction, assumed direction is correct or not, because if the result is negative, meaning your direction is incorrect, but if it's positive, then your direction is correct. So, but the magnitude is just the same. Okay, and then we have for the vertical component, y component of 52 Newton load, its moment about A is clockwise, so we will be using a negative sign convention for that. Then, so again, moment is equal to force times distance. So this force times perpendicular distance about point A is 300 mm, or we have 0.3 meters. So we'll be using Newton meters. And then for its horizontal component, okay, since its horizontal component passes through or coincides, the line of action coincides point A, so its horizontal component does not have moment about point A. Next, we have the 30 Newton force. So for the downward force, this is 30 sine of 60 degrees. So its rotation about A is also counterclockwise, so that would be negative. Negative force times distance, that is 0.3 plus 0.4 meters. Okay, so this the total distance about A, 0.3 plus 0.4. So its horizontal component, okay, does not have moment about A, so it will be not it will not be part of the equation. So we now have, this is now equal to 0. So the value of MA is equal to, okay, so let me use my calculator at the side. We have 52 times 12 over 13 times 0.3 plus minus, or then we have 30 sine 60.7. Okay, this is negative 8 Newton meters. Okay, okay, so since the result is negative, it only means that our initial assumption for the direction of MA is incorrect. Okay, so therefore, MA, the magnitude of MA is still 8 Newton meters. So what you will do is, in giving the final value, you get rid of the negative sign and then you provide the correct direction. So since the result is negative, meaning this direction is incorrect. So it's really not clockwise. It's rather it is, the correct direction is counterclockwise. So we will just correct the drawing. So we'll have this one. Okay, the correct direction is clockwise. So let's see what if MA, assuming, what if your assumption, initial assumption is correct, that MA is MA is counterclockwise. Okay, so what will happen in the equation is that since it is now counterclockwise, so we write MA in the equation as already positive, unlike here that we wrote it as a negative value. So you, in referring to the sign convention, that we give positive sign convention for counterclockwise movement. So since our initial assumption is that it is counterclockwise, so we write positive MA. Then we have minus 52 12 over 13.3. Still, this is negative because this is a correct rotation. It's negative. Then minus 30 sine 60. And we have 0.7 plus 0. So what you get from this equation is a positive value of MA. Directly a positive value of MA. Now this means that since the result is positive, meaning your assumption wherein MA is counterclockwise is correct. So okay. So these are now what is being asked in the problem. So the reactions at the support of the wrench. So always provide for support reactions, you always provide the direction. Okay, next, have the homogeneous 120 kilogram wooden beam is suspended from ropes at A and B. So we have here ropes A and B attached to it. A power wrench applies the 500 Newton meter clockwise couple to tighten a bolt at C. So there is actually a bolt here, and then there is a wrench applying a 500 Newton meter at this bolt to tighten the beam. So before we proceed to analyzing this example, so we are actually going to have to determine the tension in the ropes. That is at A and B. So before we proceed, we'll have to draw first the FBD of the beam. So since we're going to draw the FBD of the beam, just draw the beam and then we write and then we replace all of the supports with the support reactions. So since at this point there is a cable or rope attached, so there is a tension here. So let's say this is T sub A, meaning tension at the rope at A, and here there is also a tension. We have TB, then this is 500 Newton meters. And aside from that, even though it's not part in the initial drawing, it is said here that the wooden beam is 120 kilogram in weight. So at the center of gravity, there is actually 120 kilogram weight. Okay, now before we proceed to solutions, we have to convert kilogram is a unit of mass. So we have to convert it into weight. So we know that weight is equal to mass times gravitational acceleration. So we multiply it with 9.81 meter per second squared, which is the gravitational acceleration in SI unit, so that it will be converted into newtons. So we remember that 1 kilogram times meter per second squared is equal to 1 newton. So kilogram times meter per second squared, we have value of newtons 120 times 9.81. That is 1177.2 newtons. Okay, so we do not incorporate mass to forces. We have to convert it into weight before we incorporate it with forces and moments or torques. So in this case, okay, since this is center of gravity, so it is at the middle. So the whole length of the beam is 6. So therefore here this is 3 meters and this is 3 meters. Okay. And this is 4. This is 2 meters. Okay. So what we are going to do is, in the 3 equations of equilibrium, okay, this is useless. Could not use this because as you can see in the FBD, there are no horizontal forces. Okay, so it's okay because we only have 2 unknowns and we still have 2 equations left. So for summation of it would be easier if we are going to use summation of forces y equals 0. Okay, we'll have TA plus TB, okay, upward forces positive, that is equal to minus the downward force, which is 100, the weight 1177.2 equals 0. Okay, so in this equation there are still 2 unknowns. We could not get any value from here, but when we are going to use sum up moment equals 0, okay, if we're going to sum up moment at A, of course TA will not be part of the equation because it does not have moment at this location. So try to sum up moment at A. Okay, so we'll use the sign convention positive for counterclockwise moments. So we have for TB counterclockwise to A, so we have 4 TB, 4 being the distance, so we have force times distance. Okay, then for the 1177.2 weight, okay, the rotation to A is clockwise, so negative 1177.2. Perpendicular distance is 3 meters. And then we also have a couple here which is clockwise, so 500 Newton meter. So we use negative 500 Newton meter because it is clockwise. And remember, in our sign convention, positive for counterclockwise, so negative for clockwise. Okay, you do not have to multiply distance in moment because this is already a moment value. We only multiply distance for forces. So we have force times distance, force times distance. This one is already a couple or a moment, so you don't have to multiply distance. Okay, so therefore we could get TB, so we'll have Just use shift solve. (1007.9 newtons). Okay, so for TA, okay, you could use this equation. We have TA plus TB. We know that it's 1007.9 minus 1177.2 equals 0. So TA is therefore equal to 1177.2 minus 1007.9. That is 169.3 newtons. So there you go. These are the tensions on the ropes attached on the beam. Okay. There. Okay. That's it. By the way, there's also another approach. You could also use sum up moment at B equals 0. Okay, because if we're going to sum up moment here, we directly get the value of TA. So let's just check for TA, rotation to B is clockwise. So negative, okay, distance is 4. So negative 4 TA. Okay, and then you have positive for the weight to TB. That's so you have 3 minus 2. So this distance is 1 mm, 1 meter. So positive 1177.2 times 1. Then what else? The couple 500 Newton meter, which is clockwise, so negative 500. So this is equal to 0. So TA here still is, okay, you'll have negative 4x plus 1177.2. Okay, then minus 500. Okay, still 169.3. So this is the advantage of the summation of moment equals 0, because you could actually sum up moment anywhere in the system. Okay. Next, we have this example. Let's have this one first. So, a 250 Newton uniform beam supports loads as shown in the figure. Determine the support reactions at A and C. So, remember, okay, for every pin support, hinge support, there are two support reactions. We have one perpendicular to the surface and the other one parallel to the surface. So, since this is A, okay, rather this is C. So, this is A, Y, vertical reaction, and then horizontal reaction. So, the directions of AX and AY are initial assumptions. Then, for every roller support, there is one type of reaction, which is the one perpendicular to the surface. So, let's say this is CY. So, we are going to determine value of AX, AY, and CY. Okay. Now, as you can observe here, you have what you call, this is a distributed load. Okay. So, for every distributed load, the unit is unit of a force per unit of length. So, it could be pounds per foot, or pounds per inch, or kilonewton per meter, or newton mm, or newton per meter. Okay? Now, remember, newton times meter is not equal to newton per meter. Okay? So, this is 30 newton, meaning the intensity here there is a load that is distributed along this length, and the intensity of that load is 30 Newton per meter. So every time there is a distributed load, what we do is we convert it into a concentrated force. So if the distributed loading is rectangular, okay, what we do is that for its intensity, let's say the intensity is y, and the whole distribution length is x, okay, now its resultant concentrated load, say this is r, okay, this is equal to the area of the load. So area of a rectangle is base times height, so this is equal to x times y. Okay, so therefore if you're going to redraw this beam, okay, again for this beam, okay, there is a y here, a x, and then here cy, okay, and then we have also here a 15 Newton load. Okay, so this is 2 meters. So initially we have here a distributed load. Okay, now in converting this into a concentrated load, okay, concentrated load always acts at the centroid, or rather centroid, yeah. Okay, so we all know that the center of a rectangle is just in the middle, somewhere right here, but still the downward force will be all the way downward. Okay, so in this case, okay, it is located midway the length of the distribution. So in this case we have x over 2, this is x over 2, so the whole distribution length here is 4 meters. So therefore side by side it is located 2 meters, and then at the other side it's also 2 meters because it's a rectangle. Okay, so the intensity is the area, so we have 30 times 4, so we have 30 Newton per meter times 4 meters. This is the area of the rectangular distributed load. So meter per meter we could erase and then cancel. We could have 120 newtons. So this distributed loading is equal to 120 Newton concentrated force or load. Okay, and acting at the center of the distributed load. Okay, so we could now continue with our solution. So for AX, we need to use sum of forces x equals 0. We have AX, and then we don't have any other horizontal forces, so this is equal to 0. So there is actually no horizontal reaction at pin at A. Next, we have, okay, what I wanted to do is, since we already have AX, what we are left with is AY and CY. So instead of using summation of force Y, I would like to use summation of moment at A. We will sum up moment here so that we will be able to get CY. Okay, so it is intentional that we sum up moment at A so that AY, since it acts at A, it does not have moment here, and it will not be part of the equation here. So let's have counterclockwise positive. So for this concentrated load, we have 120 times perpendicular distance 2. So since it's clockwise, we have negative 120 force times perpendicular distance 2. Okay, again negative because clockwise. And our sign convention is positive for counterclockwise. For the 15 Newton load, again this is 3 meters. Okay, so we'll have 15 Newton load that is also negative clockwise to A. So force 15 Newton, then distance would be 3 plus 2, 5 plus 2, 7 meters. Okay, then what else? We have this one, Cy, moment about A. Okay, that would be positive force times perpendicular distance. So all in all, this is 9 meters. Okay, we no longer have any other moment or force that has moment about A. So this is all that there is. So that equals 0. So Cy therefore is 120 times 2 plus 15 times 7 all over 9. So Cy, okay, 120 times 2, 15 times 7 over 9. 38.33. Okay, upward reaction. So since the result is positive, meaning it is correct that Cy is really, our initial assumption of the direction of Cy is correct, which is it is really indeed upward. So for summation of force Ay, we already got this, so we only have Ay left. So since there are no other unknown vertical forces, so we could now use summation of force y equals 0, so upward for positive forces. So we have Ay as positive, and we have minus 120, minus 15 to the two downward forces. By the way, I forgot about the load. Meron pa pala dito sa gitna. 5, 4. Napaday ko andiri. Weight 250 Newton at the center. So this is 4.5 meters. This is 4.5 meters. So you don't have to convert this, you don't have to multiply to gravitational acceleration, because this weight, this Newton is already unit of weight. Okay, it's no longer mass, so you don't have to convert it to weight because it's already weight of the wooden beam. Okay, so we have to include it here. So there is actually 250 Newton. Okay, this is 4.5. Okay, so ito yung usually na problem. This is usually the problem that there are times that we tend to forget about the given weight of the body. Okay, sometimes it is not part of the original figure, but it is just stated in the problem. So we have to be careful with that. Okay, so anyway, so meron pa pala ditong, we'll just add for 250, that's minus 250 times the perpendicular distance is 4.5. So meron pa tayo dito plus 250 times 4.5. So the actual value for Cy is okay. So this is actually 163.33 newtons because it's a force. Okay, then minus 120, we have 15 downward. Cy is positive, plus 163.33, and the weight is downward also, so minus 250. Then is equal to 0, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so Ay therefore is, I have 20 plus 15 minus 163.33 plus 250. Alright, this is 221.67 newtons. So since the result is positive, meaning we are right with our initial assumption that AY is upward. So since the result is positive, it is indeed an upward reaction. So these are now the support reactions. And then AX, which is equal to 0. Okay. Next one is this one. Okay. So the homogeneous bar AB weighs 30 pounds. So this is the original figure. Now, in the original figure, it was not part of the drawing. The weight was not part of the drawing. So, for our solution, of course, we'll have to include the weight, even if it's not included in the original drawing, since it is stated in the problem. So, of course, at this right here at the center, there is 30-pound weight of the beam. Determine the magnitudes of the forces acting on the bar at A and B. Okay, so since in this bar or beam, there is a pin support here. So in every pin support, we have two reactions. The one perpendicular to the surface of the pin support, and the other one parallel. Okay, and then this is a roller support, so we only have one reaction, the one perpendicular to the surface of the support. So this is, let's say this is B sub Y. Okay, so we have three support reactions. And then the only loading that this bar carries is a triangular load. So how do we convert this? Okay, we have to convert this into a concentrated load. So if your distributed load is, this is what you call varying load. Okay, varying load meaning along the length, the intensities of the forces vary. Okay, so here it's 0 and then up to a certain highest intensity. So it is given that this intensity right here is 120 pounds per foot. Okay, and then the total length of the distribution is 9 feet rather. So since it's triangular, okay, this will be the location of its resultant. Okay, now for a triangular load, here we have here, then we have a location. So we have location from the vertex and or acute angle, and location from the right angle. So the location from the acute angle will be 2/3 of the base, and in this case that is 2/3 of the whole length, which is 9 feet. So it is equal to 6 feet. Okay, here from, if you measure, or if you want to get the location of the resulting or equivalent concentrated load from the right angle, it's always 1/3 of the base. So from here, 2/3 of the base. From here, 1/3 of the base. Okay, so this is, syempre kasi triangular yan eh. So dito talaga siya mas prone yung kanyang resultant, kasi dito mas malaki ang intensity kontra dito. Anyway, 1/3 of 9 is equal to 3 feet. So ganito siya. So ngayon, kung i-redraw natin yung FBD ng bar, this one, we have this one, if you're going to redraw it, so instead of having the triangular load, okay, we instead replace it with a concentrated load. Okay, now the intensity would be just simply the area, no? So area of the triangle is 1/2 base times height. So you have 1/2, the base is the 9 feet, and then the height is the highest intensity right here, which is 120 pounds per foot. So this is equal to times 9, 540. 540 pounds. Okay. So we have, okay, so this is 540 pounds. So from here, so again we have here AY, AX, and then have here BY, and this is A, this is B. Then of course we do not forget the weight, which is 30 pounds. Okay. So itong pound weight in pounds is already unit of weight. Okay, and then 1 pound is equal to 1 slugs feet per second squared. So we no longer have to multiply this to gravitational acceleration because it's already this is already the weight. It's not yet it's not mass, it's already weight. So again, the location, this is since it's in the center, so from A this is 4.5 feet, and also from the other sides 4.5 feet. Then again, for the equivalent concentrated load of the varying load, okay, again from this is 6 feet from here, and then from the other side it is 3 feet. Okay, so I think it would be best, okay, automatic, our AX is 0 since using summation of forces x equals 0, since there are no other horizontal forces aside from AX, automatic AX is equal to 0. Now for if you want to get AY, you could sum up moment here so that BY will not be part of the equation. So I say I want to sum up moment at B, positive for counterclockwise moment. So since AY rotation to B is clockwise, we have minus AY times perpendicular distance 9 feet. Okay, then for this concentrated load, rotation to B is counterclockwise, so positive 540 pounds. Then perpendicular distance to B is 3. And then for the weight, okay, rotation here is also counterclockwise, so it's also positive 30 times 4.5. So no other moment about point B, because BY will not be part of this equation because BY does not have moment about this point or about B. So we now have equals 0. So vertical reaction at the pin support is 540 times 3 plus 30 times 4.5. We divide it by 9. Okay, you have 195 pounds. So it is an upward force. Okay. And next we have A. Or we could use na lang summation force Y para we don't have to get moment. So positive, so upward forces, AY is an upward force. 30, it's the downward force, so minus. Another downward force, this is 540. Negative. Okay, we replace AY with 195 because we already have value for AY, which is 95. So positive because it is upward. Then BY is also positive. So we don't have all 1, 2, 3, 4. So we only have 4 vertical forces. So 1, 2, 3, 4. So this is equal to 0. So therefore, BY is equal to, we have 540 plus 30 minus 185. This is 375 pounds. Also an upward reaction. So you have 3 support reactions. This one, and then this one. Okay. Another one. Second to the last example. A homogeneous bar AB weighs 150 newtons. Determine the magnitudes of the forces acting on the bar at A and B. So 150 newtons, so it is located here at the center. So we'll just draw. It should be part of our FBD. Okay, let's have just draw the bar separately. Okay, so at this point there is contact with a frictionless surface. So frictionless, we have to neglect friction. So since the surface here is vertical, so perpendicular to that is a horizontal line. So this is the reaction at B. Okay, and here we have pin support. So we both have perpendicular and parallel reaction. Okay, and again we also have the weight 150 newtons, so it's at the center, applied at the center. Okay, so since the total length, okay, the angle is 60 degrees, and then the total weight is 12 feet. So this one is along the bar, it's only 6 feet distance. Okay, so okay, we're going to get AY, AX, and RB. Okay, so I guess it would be a lot easier for us to sum up forces here, because moment rather here, because if we are going to sum up moment here, AY and AX will not be part of the equation. It's only RB, the only unknown that will be part of the equation if we are going to sum up moment at A here, right here. Okay, so positive again for counterclockwise moments. So RB counterclockwise here, so that's positive RB, and then this is the line of action of RB, so this is the perpendicular distance about point A, and this height, okay, this height is equal to, okay, we have 12 here, then we have 60 degrees, so this is 12 sine 60. So that is the perpendicular distance of RB about A. Okay, next, we have the 150 Newton weight. So rotation about A is clockwise. So we have negative force 150. Perpendicular distance is this one. So this is 60 degrees. So therefore this is 6 cosine 60. So that is a perpendicular distance, 6 cosine 60. Okay, about this point. Okay, no other moment about this point, so this is 0. RB therefore is, okay, we have 156 cosine 60. Uy, naka-radian pala ang calculator ko. Okay, for our previous problem, okay, let me just correct this one because I didn't haven't seen my calculator. It's actually in mode radian kanina, so it's now in degree. Oh, let me just correct this one. 52.5 over 13. This was our previous example. So 5, this is 5 newtons. Still positive. Okay, here it's not 38. This should be. So it would be important for you to like check my calculations using your own calculators. So this should have been 73.98, and then this should not be equal to 8, rather to 12 over 13.3 plus 30 sine 60.7. Okay, 32.59. Okay, kinure ko lang kasi here no problem because we don't have trigonometric functions. Okay, let's proceed. We have 150 times 6 cosine 60 and then 12 sine 60. Hmm. 43.3 pounds. Okay. Next, we're done. Sum of forces x. So we have two horizontal forces AX and RB. So you have AX minus RB 43.3 equals 0. So AX is equal to RB, which is 43.3 pounds. This is to the right. Summation of force y equals 0. So we have AY minus 150 equals 0. So AY 150 and then upward. So we already got that. 3 reactions. Okay, last. Okay, mass of the beam. Compute the reactions at A. So there's no mass of the beam. Okay, so we have a triangular load. We convert it into a concentrated load. So we have 1/2 times 1 height. Base is this one, 6 meters. So this is 3 kilonewtons. Okay, so we get rid of this load. We use this one, concentrate. So for the distance from here, 1/3 of the total length, 6 meters. So this is 2 meters. Okay, so here we have only one reaction for the roller support. Let's say this is A and this is B. Okay, AY, and then here at B, pin support. So you have two reactions, BY and let's say BX. So this is equal to 0, sum up forces. X equals 0. So this is the result. BX is equal to 0 because there are no other horizontal forces. So we will sum up moment at B. So we will be able to get AY if we sum up moment here. So sum up moment here, BY will not be part of the equation. So we have AY negative, distance 6 plus 6, so we have 12, total distance 12, clockwise, so negative. For 2 kilonewton upward force, we have negative 12, 2, then clockwise, so total distance is 9. Then this load 3 kilonewton plus 3, counterclockwise to B, distance is 2. So thus we have 1, 2, 3. Okay, we have only 3 moments about B. 0. So AY equal to 18 minus 6 over 12. 18 minus 6 over 12. Negative So, AY equals negative 6 minus 18 over 12. Negative 1 kilonewton. So, since the result is negative, AY is, we get rid of negative sign, 1 kilonewton, and then it should be downward. So, let's correct this. Meaning, since the result is negative, this is not upward. It should be downward. So, our initial assumption of the direction is wrong. Instead of upward, it should be downward. Yan. So, next, we only have last one, by. So, we could use sum of forces. Y equals 0. Upward forces positive. So, we have by. And then, for AY, we use the downward. Since it's actually downward, so it's negative. And then, the magnitude is 1. Okay, then we have upward force 2 kilonewton. This one, upward, so positive. Then we have, we still have 12 kilonewton meter at this point. So, it's also part of this equation. Okay, let me correct that. So, since it's counterclockwise, so we have positive 12 equals 0. So, this should have been minus 12. Okay. 18 minus 6 minus 12 over 12. Oh, this should have been equal to 0. So, AY is 0. Okay? 0 pala ang Y. AY. So, anyway, yung BY, negative 1. So, this is 0. Yung BY, upward, downward 3. Ito, downward. Up, 1. Ito, upward 2. So, dalawa lang. 0. So, BY is equal to 3 minus 2, 1 kilonewton. So, it's positive. So, we are correct that it is an upward. Okay. So, these are the answers. Where BY is 1. And here, this is 0. And horizontal reaction, B is also 0. So, that's it.